All right, so here we are looking at the free response from Monday. For the first couple, they just give you some p-values up here and some x-values to plug in here and asking about convergence. So the first two are going to follow pretty similarly. The first thing we want to do is take these values and substitute them in for x and p. So the nice thing that we hopefully notice here is that we have an 8 minus 3 to the n and a 5 to the n, which are going to cancel out, giving us a simple alternating series. As I hope you remember, when it asks about converging absolutely, conditionally, or diverging, the first thing we want to sort of see is if it converges at all. Now, this series here I would compare to a p-series, because except for the alternating part, if we think about this just as the absolute value for the absolutely convergent, that absolute value gives us 1 over n to the third, which is a convergent p-series. Because the power here is -3, which is less than -1. And now, because we see that we have a convergent absolute value of this series, that means that it converges absolutely, which is how you get this answer. I haven't written out a full complete answer here. If you want to see a complete sentence, you can look on AP Classroom, since there's not a ton of space here. Let's look at Part B. Alright, so Part B starts out very similar. We have two values for p and x that we're going to substitute in. And just like as before, we see that we have a 5 to the n, and we're going to have 5 to the n in the numerator and cancels. And now, hopefully, we see a familiar friend. It's our friend, the alternating harmonic series. Now, if you recognize it, this is enough to say that this converges conditionally if you can state that you recognize this as the alternating harmonic series. Remember, converges conditionally means that this series here converges, but the series produced by the absolute value does not. So remember, alternating, famously convergent, not alternating harmonic, famously divergent. And since this one diverges, but hopefully we all have memorized by now that this one converges, that's how we arrive at this conclusion. All right, Part C is a little bit more challenging. They're giving us an x value, but we need to find the values of p, and then as always explain our reasoning. So I'm going to start by plugging in that x value. All right, so the first thing that we see when we plug in is we're going to get a 5 here, but we're not going to get a 5 the nice way we had before. We're actually going to get a -5. So we can't just cancel these two out like we would before. We're going to have to deal with this negative, and we can do that by factoring, but remember that that negative is also being affected by the n. So when we factor, they both have the -1 from the negative to the n and then 5 to the n. These we can cancel out, and then these we can combine because they're powers of -1. So we're going to add those exponents. And 2n plus 1 here is our new exponent. This is always an odd number. No matter what you plug in for n, you're going to get an odd number there. And so we can simplify the numerator to just -1, because -1 to any odd power stays -1, just like how to any even power would be +1. So the values of p that we're potentially looking at are these negative terms down here. So I erased a little bit. Here we've got our power series. If you've gotten this far, you've already gotten half credit. Here we're looking at a p-series. So the negative here isn't going to affect its convergence, just like a coefficient isn't going to affect convergence in an integral. So we're really just looking at this single value of p here, and as long as that value follows your p-series rule, that's going to be fine. So in this case, we only need this in order to converge. We just need that p is going to be greater than 1 since it's in the denominator. And you would write that out in any other sentence that you could need. Main thing, again, making it positive because it's in the denominator. All right, let's look at our last problem, D. once again, we're given a value for p and for x, and this series is going to converge to some value. Find the first two terms to approximate s using the alternating series error bound to show that the approximation differs less than 1 over 300,000. So this comes back a little bit to what we were looking at in our last free response. And we're going to start by just setting up the first two terms of that series. So there's our series. Did a little simplifying, and we're just going to plug in our first two terms using n equals 1 and n equals 2. So here are our first two terms. N is 1 and n is 2. I'm going to do, again, a little simplification. So based on our first two terms, we see that our series is approximately equal to 9 over 5 thousandths. So what we want to do is to see then what is the error bound based on that. And in order to do that, we are going to use the next term in the series, which would be the n equals 3 term. So just a heads up, I'm going to erase some stuff. So let's first write that third term. Okay, so here's our third term, and we want to remember that the error is going to be less than this. So if we simplify that big fraction, so now we know that the error has to be less than 1/375,000th. And so if we're referring back to what's given in the problem, we see that we want to know that it's within 1/300,000th, which is plenty because this is going to say it's even more accurate because the denominator is smaller. And by the transitive property, if we put the error on this side over here, we're going to end up with this is less than here, which is smaller than 1/300,000th in turn, meaning that the error is smaller than that number. So hopefully this helped clarify any questions that you might have. I'll be available by in comments, the Google Classroom, email, or Zoom from 12 to 12:45. So don't hesitate to stop by and ask.